And good day, everyone. Welcome to today's webinar on DC voltage redesign. This webinar is sponsored by A-Card Commutator of Tennessee, and this message is provided by them. A-Card Commutator of Tennessee is your senior partner for actually OEM mil-spec compliant manufacturing, refills, and repairs of all makes, all types, and all sizes of commutators and slip rings with around-the-clock operation and continuous American family ownership since inception in 1993. Customers win as a result of ACT family having 4+ centuries of collective experience from as few as 21 staff members. ACT's ensemble of experts developed benchmark standards for superior quality like actual ground protection, mica versus nothing V-rings, and active G-force certification, while collectively improving upon design and manufacturing techniques from as many as 5 other vendors. ACT's resulting unique knowledge and understanding of the real-world physical science involving matched materials choices, design engineering, and production techniques provides ACT customers with competitively priced, significant reliability and longevity advantages. Quantitative testing always beats subjective guessing, making ACT the right choice for 21st century high performance and ultra high performance applications. ACT exclusive scheduling normal production 24/7, 365 has ACT consistently delivering the world's fastest, most reliable, actually OEM mil-spec compliant commutators and slip rings, since all others, close and closed facilities don't produce. Thank you for 27 incredible years of consistent growth by making the right choice with ACT. And with today's webinar, here is Chuck Young.
Good day, everybody, and welcome. Today we'll be talking about DC voltage redesign. Before we get started, a quick reminder on how to ask questions. So the slides up here, and I think everybody should have the handout printed out. So if you need to reference back to that to see how to ask a question, why, feel free to do so. So those of you who've known me for 40 years or so know that it's not a canned presentation. So if you have a question, just go ahead and sing out and ask it, and we'll take care of it right then. Don't worry about me losing my place. So we'll go ahead and get started. So what we're going to talk about today, voltage change for shunt fields, for the armature, and for the interpoles. And the armature and interpoles really sort of go hand in hand. So we'll talk about the interpole and armature circuits, and I'll touch at 2 places on compound wound machines because they sort of fall in under fields in a lot of our minds, but really when it comes to voltage changes, it should follow the armature and interpole. So that's where we'll kind of address that at 2 spots. And then something that's really often overlooked when we do a voltage change on the armature circuit is the brushes. And the reason we care about the brushes is the current density. If we were to double the armature voltage, then we'd have about half the armature current. So the brush current density would be very low and the brushes would dust. So you really want to work with your brush supplier to address the brush current density issue. And of course, converse to an increase in voltage, if we decrease the armature voltage, then the current increases, and therefore we might actually have to add brushes, or hopefully we can address it just with a change in the brush grade. So let's talk a little bit about a real quick quality control check, or reality check, that I like to kind of keep in the back of my mind when I'm looking at DC machines. The ampere turns per pole of the fields are about 1.1 times the ampere turns per pole of the armature. And if it's a form wound armature, it's pretty easy, even without having to rewind the armature or doing anything invasive for checking data. The armature current on the nameplate times the number of commutator bars times the turns per coil in the numerator over the poles times the circuits. And we'll touch on circuits because sometimes that's really easily misunderstood. So I have a table coming up on that as well. So that's our ampere turns per pole for the armature. For the interpoles, it's about 1.2 times that number. and then for the fields, 1.1 times that. And in the case of the interpoles as well as the fields, keep in mind that we need to know what the circuits are. Were those coils connected in series where it's one circuit, or was it a two circuit, or in the case of a 6-pole or an 8-pole, we might have as many circuits as poles on a large machine. So that's kind of a good reality check for us as we go through this process. So let's start with the shunt fields, partly because that's the thing that we're most often called upon to change voltage, and also partly because they're easier and it's a good foundation for looking at how we do everything else. So these are our shunt fields. You can see it looks like these have been rewound, potted, reinstalled back into the frame, and here's just a cutaway view of a shunt field coil here. So the first thing to do is to look at it and see how easy can we make this. If your customer has 240-volt fields and they've bought this machine and they want 120 volts, then we can just reconnect them. Looks like we have a question here. Let me catch this. Okay. So Jim is asking, where do the 1.2 and 1.1 factors come from? And that's a good question, Jim. If we look at a DC machine apart, or if we can kind of visualize it assembled, we have an air gap between the armature and the interpoles, and a different sized air gap between the armature and the fields. So if you kind of view this like a transformer, if we have a conventional transformer, the primary and secondary are kind of wound on the same frame, so no worries, or on the same core, I should say. But because of that air gap between the armature and the interpoles and the armature in the fields, we're forced to kind of boost that just a little bit here. So that's where those numbers come from. It's a good quick check for us, and we should usually be in the ballpark of those numbers. Now, the reality is, depending on the size of the machine and the manufacturer, the designer, you may find that 1.2 for the interpoles is close, but it's not exact. Maybe it's 1.25 or 1.15 or something, but it should be in the ballpark. If we're off by a factor of 2 from what we expect using those multipliers, then that's a red flag for us. So back to the shunts. If it's, DC machines are quite expensive and there are a long delivery time. Unlike AC machines, a 10 horsepower DC is economically feasible, not only to repair, but even to do voltage changes and redesigns. So if we have a DC machine, your customers bought it on eBay or used equipment dealer, and everything matches his existing motor except the field voltage is not the same as his motor. Let's take a quick look and see if, for instance, we had all 4 shunt fields in series and we had 1,000 turns per coil for 240 volts, then we could simply reconnect it series parallel, in other words, a 2-circuit for 120 volts. And while it would be an oddball voltage, we could go further and connect them 4 parallel, in this case for 60 volts. So that's kind of a quick check to look and see, can we actually just reconnect it to give the customer what he needs. More often than not, that doesn't work out, but 1 out of 10, you get lucky. So you save the customer some money and quite a bit of time. So let's look at a pretty realistic one. Customer buys a spare motor and the fields for this spare motor are 240 volts, but his existing motor that's in service and the drive for that motor are set up for 300 volt fields. So if we just use an example, 1100 turns per coil, 1 number 17 wire. So remember, our turn change is always going to be proportional to the voltage change. If we increase the voltage, we're going to have more turns. If we decrease the voltage, fewer turns. So that's sort of a quick reality check to make sure we don't accidentally go the wrong direction. So if we need 300 volts and the existing rated voltage is 240, 300 over 240 times the existing 1100 turns gives us 1375 turns per coil for the 300 volt fields. Now we want the coils to fit physically in the same cross section, of course, and because the voltage has increased, the current has decreased by the same proportion. So that means we don't need as big a wire, and in fact we probably can't fit as big a wire. So if we address the wire size, our number 17 is 2050 circular mils. So if we look at our turns, our original turns of 1100 over the new turns of 1375 is 0.8. 0.8 times 2050 is 1640. So we're very, very close to a number 18 wire size. In fact, we're right at 1% from between the wire size and our calculated cross-reference here. So good to go. So that's how we would rewind the fields. So kind of keep in mind, what about amperage? Well, if we had 240 volts originally and the fields were rated for 5 amps, 240 times 5 is 1200. 1200 divided by 300 volts is 4 amps. So we know that we have the new field current rating at 300 volts is going to be 4 amps. So it's decreased in proportion to our voltage, inverse proportion to our voltage change. So if we look at the ampere turns per pole just as a double check, well, if our original had 1100 turns and it was rated 5 amps, so just multiply those together, each pole 5,500 ampere turns per pole. So let's double check our redesign. The 1375 turns times the new amperage rating of 4 amps is also 5,500 ampere turns per pole. So it's a double check to make sure we've not changed the field strength. I think most of you know that when we control DC motor speed, we usually simply do it by field weakening. So if we had lower amperage, less ampere turns per pole, a weaker field flux, the motor would speed up. And we don't want that in our base speed. So easy math here, easy double check here to make sure that we've gone the right direction. So if we look at our shunt fields, the field rated current times the poles, and we know what our total ampere turns of the fields, and we can look at what we might do with parallel circuits to change that as well. So it's kind of a double check for us to make sure that that 1.1 number for fields or the 1.2 number for interpoles, it's a pretty easy check to make just to verify that the last people to work on the motor didn't accidentally change the circuits. We have these fields here in series, and because we know they're in series, one circuit, we can calculate what our ampere turns per pole look like. We can do kind of a reality check on the circular mils per amp as well. And if we're way off by a factor of 2 or more, then that pretty good red flag that somebody in the past has accidentally or deliberately and unknowingly changed the strength of the fields. So I'm going to touch on compound fields here, and then I'm going to drill down deeper into them just a little bit further on. So when people say compound wound, well, what does that mean? Well, what we're really talking about is the percent compounding is how much of the total field strength comes from the series field. So our shunt ampere turns over the shunt plus series ampere turns gives us an idea what we've got here. So we can look at our ampere turns, 1,000 turn shunt times 3 amps is 3,000. 4 turn series times 250 amps is 1,000. So our series, this should say series ampere turns on this first line, guys. So 1,000 over 4,000 we're 25% compounded. So what that means is 25% of our field strength comes from our series fields. When we talk about percent compounding and stab shunt, which you'll often see on a nameplate versus compound wound, most people use either 15% or 20% compounded as their definition of stab shunt or stabilized shunt. And if it's over about 25% compounded, then we consider it compound wound. Now again, depending on the vintage and the manufacturer, you'll hear there's kind of a gray area there as to where that dividing line is. It's somewhere in that 15 to 20% range for most people who are talking about compound windings. So the reason I mention it here is if our customer wants to change the armature voltage, then that's going to change the armature current. And because the series fields are in circuit with the armature circuit, that means the series field strength is going to differ. So if we're doing a change in just the shunt fields, then that won't change our percent compounding. So that's an important thing to kind of keep in mind. So ampere turns per pole, and I know I'm reinforcing that multiple times, but the ampere turns per are just the current going through the coil times the number of turns. The thing to keep in mind is the actual current, depending on what our customer is doing with the motor, may not match the amperage on the nameplate at all. They may be running, at a much lighter load. You just never know. So keep in mind though that if the customer is running at a lighter load, the ampere turns per pole of the armature and the interpoles are changing proportionally. So that I think is a helpful thing to look at. And ideally, what we're looking at is we want the field flux not to be distorted, right? So if our interpoles are producing an equal but opposite force to the armature flux, as the load goes up, the armature current goes up, so the armature strength increases, but the interpoles are always changing in proportion to the armature. So if we know our customer is really only running at half load or 3/4 load, that wouldn't by itself impact our voltage redesign of the armature and interpole circuit. So if we look at the armature itself next, the turns, again, like the fields, will be proportional to the voltage change, but with the armature, we often have form wound armatures like you see here. And you can see this as sort of a single knuckle. If we had a multi-turn coil on a form wound armature, you'd see a double knuckle here. So it would be real obvious that this is not just a one-turn armature coil. So for most of what we deal with, we're dealing with a one-turn armature coil. And in this case, it looks like, well, we'd have to count the slots and count the bars and divide those. But we probably are looking at this one at a 3-section coil. And terminology wise, as with everything else in our industry, we tend to use different terms for the same things. So what I would call a 3-section armature, another armature coil, someone else might call 3 coils per slot. So another person might call it 3 elements. So you're going to have, very, different terms, but for the same thing. So that's what we're going to look at here. So again, if it's form wound, it's usually just a one-turn coil, and you can look at that knuckle and see if it's a double knuckle, if it's a multi-turn coil. So that's helpful. So count the commutator bars, multiply the rated armature current on the nameplate times the number of bars times the turns per coil. And again, if it's form wound, that's almost always 1, so it's sort of a default. So that's your numerator. and then put that over your poles times circuits. And let's look at a table here with circuits in just a couple of slides here. So the armature current is going to change inversely proportional to the voltage change. So because of that change in current, when we change armature voltage, we've got to consider the number of brushes per post or the brush grade, and sometimes have to address that. A lot of times you can work with your brush vendor to address that. So the first thing, as with the fields, is can we take the easy way out? Can we just reconnect the armature? And usually the answer to that is no, but it's always worth looking at. So for instance, if we had a 500 volt armature circuit and we looked at the armature and can tell that it was a lap simplex, then it's sometimes possible to lift the tops, move the tops over, and reconnect it as a duplex, so twice the circuits for half the voltage. So that portion sort of follows what we're accustomed to with three-phase AC motors, a 1 and 2 Y or a 1 and 2 delta. We know the one circuit is for example, 460 volts, then the two circuit would be good for half that or 230 volts. So the same thought process here. So if we can't reconnect it, which we usually can't, but if we can't, then the next question is, can we change the turns in proportion to get the desired voltage that the customer wants? If it's a multi-turn random winding, the answer is maybe. We might be able to. And as with a lot of designs, the armature, we do have the option of using odd turns, unequal turns, if that will get us to the point we want to be at. If it's a one-turn form coil in the armature, we're probably not going to be able to redesign it easily with a turn change unless we're looking at a pretty significant voltage redesign in the armature. However, if the customer needs this done, one thing we can consider is replacing the commutator with a different bar count so that we actually are changing the total number of coil segments or coil elements or coil sections in the armature. So the first thing is that low-hanging fruit. Here's a simplex lap winding. So we can see our lead comes in through here, through the coil, comes out to the next bar, to bar 2, and then the other coil connected to that bar comes around to 3, and so on. So if we can change the plex, the circuits, to a duplex, and it's not usually as easy as just lifting the tops and moving them over a bar, we probably have to rewind it, but we could change it to a duplex so that our coil comes off of bar 1 around, and instead of going into bar 2, we've moved it to bar 3. The other coil attached to bar 3 comes around to bar 5, and then around to 7, and so on. And parallel to that, we would have from bar 2 a coil coming around to 4, coming around to 6, and so on. So that would be doubly reentrant. And in this case, what we would find is after you've rewound it, is you have two separate circuits here, two separate paths that are independent of each other. So when we talk about circuits with armatures, I think it's important to just point out that, for instance, a 4-pole, which is what we most often deal with DC machines, a simplex, meaning that lap coil that comes around and connects to the very next bar, the adjacent bar, a simplex 4-pole has 4 circuits. A duplex 4-pole has 8 circuits. And unlike AC, where the poles sort of constrain how many circuits we can have, a 4-pole could have 12 circuits if it's a triplex, and so on. So we have some interesting options here. And of course, the more poles we have, the more possible options for reconnecting. So that's something worth having a look at. So let's take a look at an armature redesign that's not a simple reconnect. We have a 300 horse, 500 volt armature rated 480 amps. And by the way, this one is right out of the ESA DC database. Has 46 armature slots, 138 commutator bars. So 138 divided by 46, we know we have a 3-section coil. And because when you divide those, we get an integer, we know there's no dead coil or co-joined bars or anything that might give us problems. In this case, it's a 1-turn coil with a wire size of 0.72 by 180. And we want to know what that is because that's going to impact what we can do down the road as far as the redesign. In this case, our customer says, hey, we bought this motor, we got a good deal on it, but my existing motor is 330 volts. Can you redesign it? So 330 over 550 is 0.66. Multiply that times our 138 commutator bars, and we get 91. Well, if I count the slots, I've got 46 slots times a 2 for a 2-section coil is 92. So we want to look at those, okay? I can get exactly where they want. If it's 91, I can get pretty darn close just with a regular 2-section coil. So let's look at the two possibilities here. Well, the first thing is that this 91 won't work because we have a lap wound armature. And with a lap wound armature over about 10 horsepower, it has to have equalizers. So to equalize a commutator or a DC armature, we have to have an even number of commutator bars. So we can't say, okay, well, 91 divided by 2 pole pairs is 45 and a half. So we can't equalize it 1 to 46 and a half. So that tells us, okay, we can't get exactly to this 91, but we can use a 92 bar commutator and a conventional 2-section armature coil design. So if we go to a 92 bar commutator, now we've replaced the commutator, there's some expense there. And now we have a much wider commutator bar, so we have to consider that as well. But just in terms of looking at the coil for the same slot size, it looks like we can go with a wire size of 108 by 180. So we're going to go with 2 coils in the same width that we had 3, so we can go with a thicker wire here. So no change to the coil pitch. We have our equalizers. 92 divided by 2 pole pairs is 46. So a 1 to 47 equalizer pitch. So that's viable. So anytime we redesign the armature circuit to change the voltage, we also have to consider the interpoles. And that goes back to that 1.2 times that someone asked about. If we have interpoles and we expect about 1.2 times the ampere turns per pole as compared to the armature, then we're simply going to change our interpole turns by that same ratio as we did with the voltage. So going from 500 to 330, same multiplier times our interpole turns, and then the same consideration for the interpole wire size. But because our 500 volts times 480 amps divided by 330 gives us a new amperage of 727 amps. That means we probably have to increase the number of brushes per post, or depending on how many brushes are on the post and will fit on the commutator, we have to talk to our brush supplier, our brush vendor, and make sure that there's a suitable brush grade to handle that higher current density. So we can do most of this redesign just on a scratch pad, looking at it as a tentative before we strip out the customer's armature. So one of the steps that's often overlooked is calling the customer and say, hey guys, here are the changes we have to do. New COM, rewind the armature, rewind the interpoles, brush grade change, or possibly complete redesign of our brush package here. So again, early on question, once you have the new amperage worked out, you have the brush dimensions, work with your brush vendor and let's make sure that this looks like it's going to be a decent reality check before you strip the armature and find out we have a problem. So here are interpoles, and here's one removed. And again, the function of the interpoles. Without interpoles, a very early DC or an inexpensive DC that we rarely see, but we do sometimes run into, the armature strength depends on the load. And if the field flux is fixed, the higher the strength of the armature, the more it's going to distort the field flux. So that's what we're seeing here. If we were looking at this, this would be an armature rotating counterclockwise, and it's all about attraction repulsion. So the magnetic attracting force in the armature is attracting to one field and repelling away from the other, pushing away. So the field flux would distort and the motor would arc progressively worse. So by adding interpoles with the correct polarity, now the interpoles match the armature strength. So as we go through a pretty wide load range from no load up to about 150% of rated load, we shouldn't see any field flux distortion. And the reason for that is because the designer, the manufacturer, has matched the ampere turns per pole of the interpoles to around that 1.2 times the ampere turns per pole of the armature. So if we have an armature voltage change, there's the possibility that we can reconnect the interpoles rather than rewinding them. So if it's a 4-pole, 2-to-1 change or a 4-to-1 change is viable. If it's a 6-pole with 6 interpoles, we have a little bit more in the way of options: 2-to-1, 3-to-1, 6-to-1, and so on. And the flip side of that is the more circuits we have at the same armature current, the smaller the interpole conductor could be. So if we look at a big interpole like this, where we have a pretty large, beefy, edge-wound interpole, what we're looking at here is, well, this would be a very expensive interpole to have to redesign and either sub out to have someone do this, or we might have to literally puzzle cut so that we could assemble a coil like this from strips of copper. So it'd be pretty costly. And that's why we're more likely to see from manufacturers, and we can do it ourselves, we're more likely to see more turns of a smaller conductor. So if we look from our armature example again, 500 volt armature, rated 400 amps, and we're changing it to 330 volts, right? So our 480 volts times 138 bars times 1 turn divided by 4 poles times 4 circuits gives us 4,140 ampere turns per pole. So if we go back to that reality check, our interpole ampere turns per pole should be about 1.2 times that of the armature. So 1.2 times 4140 is 4,968 ampere turns per pole. So if I say, well, okay, if I divide that 4968 by our amperage, then we had, you can see you had about 10.35 turns per interpole if it's a 1 circuit. So if we're looking at about 400 circular mils per amp, then we'd have to have a wire size of about 1/4 inch by over 1/2 inch. So 258 by 585. That's a really big conductor to work with. So if we said, okay, what about other options? Well, if we go to a 2 circuit, calculates to 20.7 turns. So about a 189 by 400 could be used. That's a little more manageable wire size, but it's not a common wire size. So the other option here would be calculates to 41.4 turns with a 4-circuit with a wire size of 144 by 258. So in each of these cases, the 10.35 or the 20.7 or the 41.4, because of that decimal, the manufacturer can't make coils with 41.4 turns, so they have to fine tune the interpole strength by adjusting the shims between the interpole frame and the frame itself, and between the interpole and the air gap of the armature. So they're going to tweak that. So when I say 1.2, oftentimes we do the math and the 1.2 doesn't really seem like it works out to a whole number, but we'll oftentimes see circuits changed because almost any of us, if we're winding field coils and interpoles using a 144 by 258 wire, that's very manageable. It's a stock wire size, easy to work with. It's close to our ideal 2-to-1 to 3-to-1 thickness to width ratio to make it easier just to form the coils. So here we have our 1-circuit interpole path or series connection. So we can see the A1 through 1 interpole to the 2nd interpole to the 3rd to the 4th and to our brush holders and out as A2. 2-circuit, and I'm just showing these just to kind of show the differences here. So if it's a 2-circuit, our A1 is connected to 2 interpoles, goes through that interpole to another interpole to the brush holders through the armature and out as A2. And of course we could also have that 4-circuit. So just a different drawing. The previous slide, and I'll go back to it, you can see tracing out the jumpers and everything here just looks a little bit busy. So here's a cleaner way to represent a 2-circuit. So we have our A1 splits, goes through 2 interpoles in series, goes through the other 2 interpoles in series, but the 2 sets of 2 are paralleled with each other. The thing that I think is important to sort of as a reminder for us is that if we have parallel circuits in the interpoles, whether it's a 2-circuit, a 4-circuit, a 3-circuit, a 6-circuit, whatever, then there's a likelihood that those parallel paths are not going to carry the same current. So what we have to do is make sure that our brush holders of the same polarity are jumpered together with an equalizing jumper. So don't confuse that equalizing jumper with the equalizers in an armature. Although the function's similar, we're addressing 2 different things in 2 different manners. So if we have a 4-pole machine, the negative posts should be jumpered together. The positive posts should be jumpered together. And if we had a 6-pole machine, we'd have 3 positive and 3 negative posts. Likewise, they should be jumpered. And an 8-pole machine, you'd have 4 positive and 4 negative. And as with what we're showing here, those should also be jumpered together. So something that I think is helpful as a reality check and a double check to make sure we don't make any sort of mistakes is to remember that when we look at the interpole strength relative to that of the armature, that 1.2, we're really looking at a transformer ratio. And we can use AC with DC machines to do a couple of fairly simple transformer tests. First thing is we know that the turn ratio of the primary to the secondary of a transformer gives us the voltage ratio of the primary to the secondary. So likewise, the turn ratio of the armature to the interpoles gives us an expected turn ratio. If we deliberately or accidentally change parallel circuits, then we can change that proportional voltage change. So we could have a transformer that might have multiple taps, so we could have different voltage ratios. Same thing with our armature and interpoles. If we accidentally use the wrong circuits on the interpoles or the armature, but it's more common mistake on the interpoles, then it changes our expected voltage ratio. So if we kind of have in mind that we expect that 1.2 ampere turns per pole for the interpoles times that of the armature, then it follows that we should have some reasonable expectations of a quality control check of an assembled DC motor. So if we've doubled the circuits of our secondary, we get half the output voltage. So a common test, AC test, which is a transformer test, is to apply 20 volts AC to a positive and negative brush post with the DC motor fully assembled, and then measure the AC voltage between A1 and A2. And what we expect from experience is about half to 2/3 out of what we're putting in. So because our interpoles should be an equal but opposite force, in other words, bucking, then we expect half to 2/3 out. And we know, most of us, that if we put 20 volts AC into these two brush posts and we get a higher voltage out of A1, A2 than we're putting in, we know we've inadvertently created a boost transformer, and all we have to do is to exchange the leads at the brush holders. And now it becomes a buck like it should be. Now, it follows then, if my interpoles are supposed to be connected in series and someone has connected them in series parallel instead, that maybe I've got half the voltage out of what I expect. So a big difference in our voltage. So now I'm going to circle back to compound wound. And I think it's helpful to touch on what the shunt series does and what the series field does. So the shunt, really, a straight shunt motor gives us good speed control, but the speed kind of changes with the load a little bit. A series motor gives us a lot more starting torque, but it really depends on the the load to actually control the speed. So if you've ever gotten in your truck on a very cold morning and you try to start it and you hear the starter really wind up, you know that the Bendix isn't engaging, and the starter motor, because it's a series motor, just accelerates. So fortunately, you turn off the ignition quickly so that you don't wind that starter motor up and have it fly apart. And of course, the reason we use a series motor for that starter, just like we do for a winch, for example, on your four-wheel drive, is that we want a lot of torque, and we're more concerned with torque than speed control. So in a lot of applications, what we deal with is customers who sort of want a combination of the two. They want the speed control of the shunt motor, but they want some low end torque um, of the series motor, so a compound wound motor. So again, the percent compounding is the series ampere turns over the shunt plus series. And if we look at an example here, 1,000 ampere turns over 4,000 ampere turns, so it's 25% compounded. So the benefit of the shunt portion, low field current, makes for a very inexpensive field card or field supply to power the shunt fields. And because we can adjust the field voltage and current, then we can adjust the ampere turns, and it gives us good speed control. It allows applications where they might want to field weaken, for example. And of course, the series, because it's connected in series with the armature circuit, if it was a straight series motor, we'd only need one DC power supply. And of course, it gives you a lot more starting torque at the low end. So downside of each, well, the shunt motor doesn't have as much starting torque, as the load increases, the speed is going to decrease. And the series, the big disadvantage is that it can run away if not loaded. So we have to have that coupled to a load. So let's look at that and kind of think about that percent compounding. So here's what we're looking at: ampere turns of the shunt plus ampere turns of the series. And if we look at a DC motor, and this is kind of a nice schematic from your pocket handbook, you can see that the series field, because it's in circuit with the armature and the interpoles, if we're running this in the service center uncoupled, then there's very low amperage going through the series. So the higher the percent compounding, the more our series field strength comes from the series. In other words, our total, our shunts ampere turns plus the series ampere turns, the more of that total comes from our series fields, the weaker our fields are compared to what they're designed for at load. So we might have our rated field current, so we have our shunt ampere turns all being developed, but our series field is not developing very many ampere turns at all when we're running uncoupled. So the higher the percent compounding, the more of the field strength comes from the series, the more we're running really in a field weakened condition. So instead of an uncoupled DC motor running about 10% over our base speed, we may find that we're running 20 or 30 or 40 or 50% over our rated base speed. Doesn't mean we've made a mistake in our rewind at all. It simply means that we have enough of a percent compounding and our series is not contributing to our total field strength until we have a load on the motor. So if we're doing a redesign, if it's a voltage change of the armature circuit, in general, if it's less than a 10% change, you're probably okay. If we've halved the armature voltage, we may have to reconnect the series in twice the circuits so that we have not only the correct ampere turns per pole from the series, but also so we have twice the conductors in parallel to handle the higher current associated with the lower armature voltage. Otherwise, you're looking at doing a proportional turn change and wire size change, just as you did with the interpoles. So again, ballpark 15 to 20%. Most of us call that a stab shunt or stabilized shunt. If it's over about 20 to 25%, then it's compound wound. And the other final caution is that if it's over 50% compounded, meaning more than half of our total field strength comes from the series, then the motor could actually reverse instantly as the motor is brought up to its full load. So that's pretty dramatic. So if the customer accidentally connects it differentially instead of cumulatively, then the subtractive nature of the series field is going to cancel out more and more of the shunt field as the load is increased. So again, cumulative, the shunt field and the series field on the same pole are the same polarity. So the ampere turns from the two are additive. Differential would mean that the series is connected to the opposite polarity of the shunt field. So the field strength from the series would be subtractive from that of the shunts. And there's only one application that we've ever run into where a DC motor would be connected differentially. So I would always expect a DC motor to be connected cumulative, and regardless of whether it's the application is cumulative or differential, the field markings are correct. So if you're checking polarity of a DC set of fields and you F1 positive and your 12 o'clock field is a north, and then S as in Sam 1 positive, your 12 o'clock field must also be a north. If it's not, then one set of those fields is labeled backwards. So we've got to give the customer a heads up here. So again, the series, almost no effect until we start to load the motor. In other words, the ampere turns contribution from the series is very low. Whatever your no load amps is, that may be 5 or 10 amps times those 2 or 3 turns. So the ampere turns per pole from the series of a compound wound motor are really low. And the higher the percent compounding, the more variation in speed we're going to see between base speed and what we're seeing unloaded versus loaded. So just quick summary, armature voltage change, we've got to address the armature, the interpoles, the series coils if present. If it's more than say 20% compounded, then we really need to look at that. And then of course the brushes as well. The shunt field voltage change, keep in mind that reconnection is sometimes an easy way to go here. If not, our turn change is proportional to the voltage change. So if we're going to go to a higher shunt field voltage, we need more turns and vice versa. And then the wire size is inversely proportional to the turn change. So with that, any additional questions here? I just threw some cool looking DC photos on this slide because it looks better than just a big old question mark. Any other questions here? Jim, you're welcome. Anybody else, any questions? You're going to give me a big head. I'm going to think I covered it all. Well, if not, our next webinar is going to be predictive maintenance technologies for the field service for service centers. And we've got another question up here. Okay, thank you. How about the armature core? Does it have no effect in change of armature voltage? It's a good question, Jerry. The armature core doesn't have any effect on change in armature voltage. We're still dealing with ampere turns per pole. So as such, that means our armature flux is going to change in proportion as well. So if, for instance, we had an armature core running at say 80,000 lines of flux per square inch, then changing the armature voltage because we're changing the turns and the voltage in proportion is going to maintain that same level of flux. And of course, it's a little bit interesting simply because when you look at the armature, as we change the voltage and the speed, the frequency also changes. So, but no effect of the armature core with respect to that. Jeremy's going to put me on the spot. Okay, the application of a differential compound motor. The only one that I can recall ever encountering was stamp press. So usually we're seeing a stamping press or punch press with the design D as in David motor and oftentimes with a flywheel. But in very rare cases where you see DC machine on a punch press, that's one where they use a differential compounding rather than cumulative. So kind of a little bit of an oddity, but you guys run into everything out there. So that's what we have. Okay, so our next webinar will be Wednesday, September 15th. Gene's going to talk about predictive maintenance technology. So good field service stuff, an area that a lot of us could get more into. And then tomorrow you'll be emailed a link to a survey so you can provide feedback on the webinar here. Someone else has asked on some mill motors where they've changed the voltage Okay. Yeah. I think I'm understanding. On some mill motors I've seen where they change the voltage from 240 to 300, or maybe a 500 volt armature upgraded to 700. Can you just add the voltage, or do you need to do something with the series fields? What I would address there, Bob, is I would take the time to look at the percent compounding. So the series turns times the armature current, and then consider the circuits if it's not straight series, and then the shunt fields ampere turns. And if you're under 10 or 15% of the total field strength being from the series, then you really are unlikely to see any sort of problems with just using the same series that you had. If it's a motor with a fairly high speed range, let's say from the base speed to the field weakened speed, then in a case like that, I would really be cautious and go ahead and redesign the series fields just as you do the interpoles to correspond with the change in the armature voltage. Any other questions? Okay, well, I think that wraps it up. Thank you everyone for attending. And again, with the work that's going on with the ESA website right now, it might be 2 days before the link is up, but you should be able to use the link, review it, and be in good shape there. Thanks very much.